Good morning, everybody. We're back. Now we're going to be talking about instantaneous velocity or instantaneous rate of change. So in the previous section, we were discussing average rate of change. And what we're looking at there is the average velocity of our vehicle over the course of a 4-hour trip. Okay, we were able to find that by basically just doing a quick slope evaluation where we found our distance covered at the end of the trip, the amount of distance we had covered at the start of the trip, which was 0, over the time that it took us to do the entire trip minus 0. We did the average rate of change, which we said was f of b minus f of a over b minus a, and that works for all functions, okay? So that gives us the average rate of change, or the average velocity, if we're specifically talking about a particle moving, over a set interval, all right? There's a starting value and an ending value, but they're not the same value. Okay. What we're looking at now is what is our instantaneous rate of change? Or if we were to put it in terms of particle movement, what's our instantaneous velocity? Okay, so if we go back to our trip to New York City from the previous section on average rate of change, right? We found the average velocity over the course of the 4-hour trip. What if we were instead interested in the velocity at one single instant? Okay, what if we were interested in knowing what our car's velocity was at the 3-hour mark, right? So we have a timer going, we start the timer when we pull out of the driveway, and then at exactly 3 hours later, how fast are we going, okay? Now, if we're in the car, that's easy to do. We just take a look at the speedometer. The speedometer tells us exactly how fast we're going at exactly the 3-hour mark. We don't have that available to us. What we have is our position graph. I didn't label the axes. I apologize for that. That's bad math on my part. But this is our position function. I just put down the important data there. So we have the distance from home here on the vertical axis. We have the time elapsed here on the horizontal axis. Okay, so we don't have a a velocity graph. We have a position graph, and we're trying to figure out what our velocity is at exactly the 3-hour mark. Right? So initially, people want to say, okay, well, let me go to the 3-hour mark. And if I go up, I see 180. Right? Well, it makes no sense that we were traveling 180 miles per hour at the 3-hour mark, which is true because this is not our velocity graph. This is our position graph. I should probably label that. So let's do that. This is our position graph. So the 180 is not our answer, okay? Because that's how far we've traveled, 180 miles up to the 3-hour mark. We want to know how fast we are traveling at the 3-hour mark. And the way we're going to get around that, the way we're going to try and figure it out is since we can't find it, we're going to try to approximate it. Say, okay, well, what data do we know? Well, we do know that we've gone 180 miles at the 3-hour mark. And we do know that we've gone 130 miles at the 2-hour mark. So we could do an average velocity, because we have 2 data points. We could do an average velocity from the 2nd hour mark to the 3rd hour mark. And while it would not be exact, it would be an approximation. So let's do that real quick here. So what's the car's velocity? We can't find it. We don't know. It's not possible to find it based off of this data. But we can approximate it, all right? We can approximate it doing an average velocity. So we can take our data points. And we know that we have 2 130 and 3 180. So let's take those, and we can say 180, which is our second y value, just like we did in the previous example, minus 130. Over our x values, 3 minus 2. Okay, so our average velocity during the hour preceding the 3-hour mark was 50 miles per hour. So we were probably going approximately 50 miles per hour at exactly the 3-hour mark. But we don't know for sure. It's just an approximation. And that's the best that we can do off of our data. We could do a little slightly different. We took the hour prior to the 3-hour mark. We could also take the hour after the 3-hour mark. We have one more data point here. Over 4 up to 20. We could also have approximated, because again, it's approximation, so there's not one exact answer. We also could have approximated by doing the hour after the 3-hour mark. That would be 220 minus 180 over 4 minus 3. Which would give us 40 miles per hour. So we know that we average 50 miles per hour before the 3-hour mark, that 1 hour beforehand, and we averaged 40 miles an hour after the 3-hour mark for 1 hour. So perhaps if we take those two and we average it, we get 45 miles per hour. Maybe that's a little bit better of an approximation. We don't really know because we're just so far away. So let me ask you this question. What, and this is in your notes as well, what information is needed in order for us to get a better approximation? And if you're thinking about this and you're thinking, well, you know what, it would be nice to know what's happening as we get closer and closer to t equals 3, that is correct, okay? We would like to know more about what's happening as we are near 3, because this is an hour away. What if we were only a half an hour away, or 15 minutes away, or even better, 15 seconds away, all right? Or 1 second away. That would be a lot better. So that's where we're heading. But before we do that, let's do one more generalization, because we just did instantaneous velocity. In the next video, we're going to broaden this out to an instantaneous rate of change.